All right, so just as a stepping stone to solving problems involving net torque, I wanted to just go through an example of actually just calculating the net torque on an object before we actually relate it to I and alpha. So we recall that our expression that we're dealing with now, our equation, is that the net torque on an object is equal to the product of that object's moment of inertia and angular acceleration. So in order to solve for the net torque, I'm going to do this the same way I've solved for the net force previously. I'm going to solve for all of the torques on an object and then just add them together, keeping track of my positive and negative torques, just like I kept track of positive and negative forces. Now, the first step in solving for the net torque is to find the torque produced by each individual force. And if you recall, we solved for the torque produced by each of these forces in my previous video on torque. So I'm going to bring those values over from that video now. If you haven't watched that video and you're not sure how I got the torques for each of these forces, please go back and watch that video before proceeding. Here are the torques we calculated previously. All right, and just as a brief reminder, I made each of these torques positive and negative based on this orientation that my counterclockwise direction was positive and my clockwise direction was going to be negative. And so recall, each torque is given a sign depending on how that torque alone would cause the system to rotate. The torque produced by force A is a positive 1200 Newton meters because it would rotate the system counterclockwise. The torque produced by force B, once we got that perpendicular component, right, was negative 2078 Newton meters because it would rotate the system clockwise. And the torque produced by force C is a positive 2546 Newton meters. There was no torque produced by force D because it acted parallel to the lever arm. There was no component of force D that was perpendicular to the lever arm. All right, so once you've solved for the torque by each force, all you have to do is add them up. So my equation for the net torque would look like this. The net torque would just be torque A plus torque B plus torque C plus torque D. And if I plug in my values, it would look like this. Again, keeping track of your negative signs when appropriate. And therefore, my net torque would be 1,668. It's going to be a positive Newton meter. So now you see this is actually very powerful because if I solve for the net torque and I see that the net torque is positive, then I know that even with all of these torques, overall, the system is going to be rotating in the counterclockwise direction. In other words, this is the product or the end result of having all these torques applied to this system. It's as if I just have a single torque of 1,668 Newton meters in the counterclockwise direction. And so now, if I knew the moment of inertia of this rod, I could also then relate this net torque to the angular acceleration that I would get as a result of producing these torques. So I just wanted to walk through calculating the net torque. It's really no more difficult than calculating the individual torques and then adding them up. So most of the computational skill here is in being able to calculate each of those individual torques correctly. Once you do that, it's just a matter of adding them together to solve for the net torque.